So let's begin by commenting over the result that we did in the last part of yesterday. We proved it, but we kind of didn't reflect it over that result. So I want to reflect over that result as well. So that, not only we prove the results, but we should also kind of realize that, a particular result is a remarkable result. So essentially what we proved is that following are equivalent. Okay? So it's like you have two norms, S norm and W norm on normal space E. Okay, so you have same normal space and two norms over it. Then following are equivalent. Number one, that so it's like a weak norm. W norm is weaker than S norm. Okay, so it's essentially it's a characterization of basically the statement. The second thing that we did is that if a sequence is converging in S norm, it will also converge in W norm. Okay? And the third part was, that the identity map, which is from E to E, with S norm into E with W norm is continuous. So that's linear and bounded. And the fourth thing that we proved was that we can find a positive constant such that the unit ball in S norm can be included in ball with the C ball or C ball in weak norm. And the fifth property is, that the infimum of S norms of those F's, which are unit norms in W is positive. Okay. So this was essentially the result that we proved in the last of it. So what are the key points of this proof? The key points of this proof is that, obviously that, all these are a characterization of a norm being weaker than other. Okay. And if you see that this 2 and 3, so can you kind of see a difference between the nature of, say for example, point 1, 4 and 5 and 2 and 3? What's the essential kind of difference that you can spot between, for example, 1, 3 and 4? I'm giving you kind of hint that 1, 4 and 5 are of same nature, while 2 and 3 are of same nature, almost. So what is the fundamental difference? So the fundamental difference is that property 2 and property, points 2 and point 3 basically are qualitative in nature. So they talk about the convergence. Okay, they are convergence and continuity. So it's kind of a qualitative property then. While 1, 4 and 5 are quantitative in nature. In other words, if you can quantitatively show this is true, or this infimum exists and is positive, or kind of inequality is true between these two norms, then, so it's like all these three properties are kind of quantitative in its nature. So the good thing about, this result is that, the convergence, okay, like this kind of convergence, which is qualitative, has been characterized in the sense of, quantitative characteristics. This is something which is pretty important. And another thing that you can basically see is that, that this property 2 and 3, which are qualitative, convergence and continuity, has also a kind of equivalent geometric meaning. I mean, if you see here, that's a kind of a geometric characterization. So we are saying that the ball in S norm can be put into a ball in weak norm, basically. So it's geometric characterization. So the result is pretty nice, that it kind of allows you to have this kind of convergence or kind of continuity, in the terms of, so it's like this convergence and continuity can be proved by establishing either, inequality, or by showing geometrically that the ball can be contained into another ball, or it can be shown that you compute the infimum and it turns out to be positive. Okay. So qualitative things have been characterized in the terms of quantitative. I think it's a pretty nice characterization. Okay, what I would like to prove in the last is that any two norms on a finite dimensional space are equivalent. This is what I would like to do next. What does it mean? It means that, when you have two norms and they are equivalent on particular normed space, this means that their topologies are what? Okay, you can't say, so there's nothing like equivalent topologies, but what we can say is that basically the compact sets and the both topologies are going to be same. So they are going to share the compact sets, which are fundamentally important. So roughly, what I am saying next is that let E be a finite dimensional. It's a finite dimensional space. Okay. Then all norms on the are equivalent. All norms E are equivalent. There will be pretty nice consequences of this result. Okay? They are going to convey, the topologies which kind of share the compact sets. So the trick is this. We know So since E is finite dimensional, so let E1, E2, and En be a kind of a canonical base at any base of bases of E. In order to prove this result, what we have to show that we need to take two arbitrary norms and we have to show that they are equivalent. But I would like to argue that it's not necessary that you should take, any two arbitrary norms and show them equivalent. What you can do is that take one norm arbitrary, okay? Take one norm arbitrary and one norm, this is simply two norm, and show that they both are equivalent. Why it is sufficient to show?
Transitive property.
We can use transitivity, for example. In other words, if this is an arbitrary norm, and I show that this is equivalent to 2, that means that any norm is equivalent to basically this 2 norm. So if I have any two arbitrary norms like this and for example this norm, and I want to show that they are equivalent, so since I know that they both are equivalent to this, so therefore they must be equivalent to each other. Okay. Because of the equivalence of norms is an equivalence relationship. So it's sufficient to show that take an arbitrary norm and prove it's equivalent to what we call the two norm. Okay? This is what we're asking. Alright. So what we will do that we shall prove that an arbitrary norm. Yes.
We are taking finite dimensional arbitrary space. So is it necessary कि जो है ना two norms के ऊपर R finite dimension?
Every finite dimensional arbitrary space we can show that it's isomorphic to KD.
With two norms.
Yeah. It's isomorphic. For isomorphism you don't need norm. You just need a bijection and something that preserves what? That preserves addition and scalar multiplication. So it must be an isomorphic. Anyway, so okay, it's a good question. That does two norms make sense in first place on finite dimensional space? The answer is yes. Okay, if you want to, for example, analyze it further, why this is the case? Because any x from E can be written as sum of I equal to 1 to n xi ei. Okay? So the two norms of such x is going to be equal to what? Series of xi square where I is from 1 to n. So it would make sense. Okay? There's nothing trouble making here. We have that. So we will prove that this arbitrary norm and the two norms are equivalent. Equivalent होने का, do you remember what's the meaning of being equivalent?
Yes, sir. C1 and C2.
There exists two constants, C1 and C2, that you can have equalities in the terms of each other. Or to show that, like, this norm is weaker than this, or this is weaker than this. Okay, so let's move ahead. Consider the arbitrary norm of x. Consider the arbitrary norm of x. So I know that that this arbitrary norm can be written as sum of I equal to and xi and eiz. If you apply triangle inequality, you can estimate this by I equal to 1 to n, xi, so it's like simply mod of xi z. Mod of xi times mod of norm of ei's. We need to be careful because it's not necessary that they must be orthonormal or so it could be any basis. Okay, you can turn it into the orthonormal, fine, but ei's could be anything. Because we are saying it's a basis of field. It doesn't mean that they all should have unit norm. And then if I apply Cauchy-Schwarz onto this, then this is going to be what? This is going to be sum of I equal to 1 to n xi square 1 half and sum I equal to 1 to n norm of ei square 1 half. Okay? And if I keep this constant as c, then this guy is what? So it's like this is equal to c times of norm of x. So it's like one side of inequality is done. You need to show that you can have a similar estimate on 2 norm in the terms of an arbitrary norm. Okay? That's what we like to show next. Now, for example, reverse triangle inequality. Reverse triangle inequality, if I, for example, compute difference of this norm must be less than or equal to what?
Norm of x plus 1.
X minus y. And, and by this above inequality, I can also compute that this is less than or equal to c times of norm of x minus y but in 2.
Sure.
What is the consequence of this observation? The consequence of this observation is that I have 2 maps. The map say KT with 2 norm into R plus and the map X, which kind of maps X onto the arbitrary norm of X are continuous. Is it the case? Not and, but like, okay, this map which is defined by as this is continuous. Continuity follows from here. Just think about it. This last inequality. then we deduce continuity of norm of x, this part basically, okay, from the last equivalent.
So this is arbitrary norm.
So in other words, if this is true in general, then I can take any sequence actually, okay, you can have that sequential definition as well. You can say take a sequence that is convergent to, xn in 2 norm. Using this inequality, you can show that that sequence is also going to converge, okay. That is, let me write it explicitly. That is, if xn is convergent to x in 2 norm, this implies that xn, norm of xn converges to norm of xn. Because you have this estimator. So if this goes to 0, then this will goes to 0.
This is an arbitrary.
And hence this is a function. Happy with this?
What's the arbitrary we have done xn converges to x or norm of xn.
Yeah. This is normal. Let me write it more explicitly. So are you happy with this inequality? This is, I'm saying define a map F from my AD, which is basically E, E into R, by that f of x is equal to norm of x. Where when I am considering this E, I am considering it with the normed space as with the 2 norm actually. I'm considering it with the 2 norm. Okay? So I'm defining this way. My claim is that this f is continuous. This f is continuous. So what is the definition of continuous function? That it maps convergent sequence onto convergent sequence. That is, if you take a convergent sequence, xn goes to x in the domain, which kind of converges in 2 norm. Converges in 2 norm का क्या मतलब है? So xn minus x in 2 norm gets to 0 as n goes to infinity. This implies f of xn converges to f of x but in R actually. Okay, this would not be R but R plus. In R plus. And what is the topology on R? R plus per? So you have this absolute actually. Usual meter. Topology used by usual meter actually. Okay? And R plus. Now what is the meaning of f of xn converges into f? So I would like to show that f of xn in minus f of x in usual metric on R is going to be absolute. Is equal to what? Is equal to norm of xn. Okay. Norm of xn minus norm of x. Okay. But as I said, this inequality is true for all xy. So by this inequality I can show that this is same as xn minus xn2 norm. Okay? But I know that you have this convergence actually. So this goes to 0 as n goes to infinity. This means that this guy goes to 0. And this means that f is continuous map. F is a continuous map. Okay. So keep this fact in hand, and I would like to get into something that we did in real analysis. I would like to recall. So consider a ball in E, a unit ball, okay, and a sphere. So how do you denote a sphere? So if this is a d-dimensional space, you denote sphere by E minus 1. Okay. This is a sphere. So it comprises of those elements of E for which the 2 norm is unit. So that's a sphere. Okay. Now we know from topology, and we also did something similar in real analysis, what we call the Hanna-Borel theorem. What was Hanna-Borel theorem? It says that a set is compact
Closed and bounded.
if it is closed and bounded. So, is it closed?
Yes.
Let me show that it is closed. It is bounded. It's bounded. You can put it in a box. So it's closed and bounded. So this is compact. Okay. By Hanna-Borel. It's a compact set. So if it's a compact set, then we can restrict this F onto this compact set. So this F is defined over whole E. So I can do what? I can consider its restriction on this sphere. Okay. So when you're going to restrict this SD minus 1 onto F, the image of this sphere, in other words, what would be the image? What we can say about the image of this sphere actually?
Closed bounded program.
So since F is continuous, this sphere is also going to be compact.
Compact.
Because compactness is a topological property. So continuity preserves compactness actually. You get it in topology. So this guy is also, what do you call, compact. Okay. So if it is compact, and there was another result actually that we call EVT. Remember? Extreme value theorem. What does it say? That if you have a compact set, image of a compact set, then you can always find the supremum and infimum, okay, of that set, within that set actually. Within that set. Okay. So it's like, a compact image under a continuous maps achieve infimum and supremum. Then by EVT, Okay? I can do what? By A with T, I can find the infimum of norms of y, those y's which are sitting in this S minus 1. Agreed that this would be the case actually. Because